All right, good day everyone. We are now on the third week of our discussion. So for this particular week, we are going to talk about applications of integral calculus, starting with volumes of solid. So before we begin, let's try to differentiate area and volumes. So if you try to look at it, area is applicable to two-dimensional objects, whereas volume comes in the moment you have a third dimension. So you now have three-dimensional objects. That's the reason why for area, the unit is in square meters because we are focusing on two dimensions, whereas for volume, the unit is three dimensions or cubic units. In this case is cubic meter, again, because here we now have three dimensions. So this is where integral calculus comes in. Let's try to recall some of the basic ways to integrate functions. So you may pause this video and try to do the following items first before looking into the answer. All right, so the first function here, the integral of 1 dx or the integral of dx will just be equal to x plus the constant c. The integral of x dx is x squared over 2 plus c. X squared dx, the integral is equal to x cubed over 3 plus c. And of course, the integral of x cubed dx is equal to x to the fourth over 4 plus c. So if you are to compare the four integrals, which do you think corresponds to volume? It's actually the third one. In other words, here, to come up with the volume, we need to integrate an area. Or integrating an area, a formula for area, results to a volume. So that is actually the premise of this particular lesson. In order for us to find the volumes of solids, we need to be able to start with a formula for area, get its integral, and the integral results to the formula for volume. So to find the volume, we need to integrate an area. Let's consider this particular example. So consider your f of x equal to cosine of 0.5x minus 1 plus 2 in the interval 0, comma 12. So if you recall, in the previous week, we focused more on finding the area under this particular curve. And if you recall, to find the area of the region under this particular curve, it will just be the integral of cosine or the integral of the function from 0 to 12. So using your calculators, you can actually compute this one. But please take note in the IBDP exam, if the points are if the points is more than 3 or even more than 5, you need to show a portion of your working before you go or before you use your calculators. So in this case, using your calculator, we can just directly compute that the area is 23.77. Since it's an area, it must have square units. Now, how do we find the area, or where did we start? Where was the beginning of using integral calculus in finding the area? If you recall, to find the area of irregular shapes, we actually divide the region into several smaller rectangles. And the idea here is adding the areas of the rectangles for us to give an approximate area of the region. And such method is actually finding the integral itself. All right. Now, we will use the same idea in order to find volumes. Suppose you are to rotate this curve 360 degrees about the x-axis. So just try to imagine having this curve. What will you get if you are going to rotate this about the x-axis 360 degrees? Give it a thought. Maybe give yourself a minute, pause this video, think of the resulting object. All right? I'd like you to compare it. So this is where the axis of revolution is. That's the x-axis. Compare it with this particular object here. So this particular object starts from a certain curve, of which the shape is the same with the curve we have here, and try to observe what happens if we rotate it 360 degrees about the x-axis. So basically, rotating this curve 360 degrees about the x-axis creates a three-dimensional object. And since it's a three-dimensional object, hence, we can already find its volume. Okay? So how do we find the volume of revolution? Take note that this 3D object started from a simple curve, rotated 360 degrees about the x-axis. So if you try to look at this one, the rectangle method is not anymore applicable since we already have a 3D object. However, if you try to look into its cross section, okay, so the cross section of this particular 3D object is simply a circle, and such circle comes with an area pi r squared. So if you try to look at it, since we rotate it 360 degrees, so somehow if you cut it in the middle, for example, you will see its cross section, which is just like a shape of a circle. And the area of a circle is computed using the formula pi times radius squared. Now, try to see what the radius is equal to. So before we go into the radius, take note that the axis at which we rotated the curve is actually the center of the circle. Obviously, it is where you rotated the circle that axis must be found in the middle of the object. So try to investigate, try to look into what the radius is equal to. So if you try to look at it, the radius is just equal to the distance from the center going to any point in the circle, or on any point on the circle rather. So we can look at it this way. So these are actually the radii, or the radius. And if you wanted to know the length of the length of the radius is just equal to the function y equal to f of x at certain values of x. For example, if you wanted to find the length of this will just be equal to this particular value of the y at this value of the x. So meaning, upon knowing the value of this x, we can put its value in the function f of x, and the corresponding y value refers or corresponds to this length, which is simply your radius. Okay? In other words, we can simply approximate the volume of this particular object by knowing the areas of the circle and adding all the areas of the circle which composes this particular object here. So basically, once we already have all the areas, okay, the area will now be processed in order for you to find the formula for the volume. So if you try to recall in my previous slide, in order for you to attain the area, or in order for you to attain the formula for the volume, you need to find the integral of the area. So we need to find the integral of the area of a circle, pi times r squared dx. Now again, the radius of this circle, if you try to look at it, corresponds to the function f of x at a certain value of x. In other words, the volume of this particular object will just be equal to the integral of pi times your function f of x squared dx. That is from a certain interval a to b. So if you wanted to simplify this further, since pi is simply a constant, we can just simplify this by putting pi outside. Hence, the volume of this solid object made out from rotating the curve along or about the x-axis will just be equal to pi times the integral of f of x squared from boundaries a to b. Okay? And this is now the formula for the volume of revolution. Let's try to have some examples for you to be able to understand this further. Let's go back to this particular example. Suppose you are to find the volume of revolution formed when the curve is rotated 2 pi about the x-axis. So again, the object form is the one you saw a while ago. So here we know that the function is equal to cosine of 0.5x minus 1 plus 2. So the volume of the solid object form will just be the integral, or it would just be equal to pi times the integral of the function squared from 0 to 12, because we're given that the interval is from 0 to 12. So if you try to simplify it in, and by using your calculators, or by using GDC, then we can already find the volume, which is equal to 167.27 cubic units. Take note, this time, since we're talking about volume, so it's now cubic units, or we say units cubed. And this is how we find the volume of the object. Let's have another example. Before we go to the example, volumes of revolution actually is formed when a continuous function is rotated about 2 pi radians, either about the x-axis in this example, but it's also possible that it will be rotated about the y-axis, which you will see later on. If it's rotated about the x-axis, the volume will just be pi times the integral of the given function from intervals a to b. All right? And evaluating it gives you the value of the volume. Take note, volumes are in cubic units. We actually call this the disk method. I will explain this later on for you to be able to see the difference of this, that with the other method. Okay? But this method of finding the volume is what we call as the disk method. Disk method from the picture itself, which is a floppy disk. Let's have another example. Suppose this is the function given intervals 0 to 4 inclusive. Find the volume of revolution formed when the curve f of x is rotated through 2 pi radians about, let's focus with letter A, the x-axis. Alright, so since it's rotated about the x-axis, therefore the volume will just be equal to pi times the integral of the function from 0 to 4. Okay, again, when you simplify this using the laws of integral, and when you evaluate it given these values, then you'd be able to see that the volume is equal to 100.77 cubic units. All right. As what I've told you a while ago, it's also possible that the curve will be rotated not about the x-axis, but about the y-axis. For example, let's have this one. Rotate the curve 360 degrees about the y-axis. So this time, you are going to rotate it about the vertical axis and not the horizontal axis. I'd like you to give yourself a minute. Try to think of what would be the resulting object when this curve is rotated about the y-axis. You may pause this video and give yourself a minute. Okay, try to compare with what you have predicted that with this illustration. So basically, it's like you are forming somewhat an object closely similar to that of a cone, wherein the upper portion is open. All right. Now take note, class, that this one is actually solid, this portion here. That means the entire portion here is also solid. Okay. So for you to be able to find its volume, we need to find an expression in terms of y and not of x. Why do you think this is in terms of y? This is in terms of y, it's because the rotation is along the y-axis and not the x-axis. Hence, we are not going to use this. Instead, from this given function, we have to express it in terms of y. So it would now be y equal to x squared plus 1. Change the subject from x to y. So by means of algebraic manipulation, we can now find the value of x as positive square root of y minus 1 and negative square root of y minus 1. Now, which of the two are you going to use? Again, look at the original graph. Try to see which of the two is being shown here. So basically, the ones that is being shown here is actually the positive root. In other words, we're going to use this function x equal to square root of y minus 1. So since we now have a function of y, we can now find the volume of the resulting object by using the same formula, but this time using y instead of x. So this would now be pi times the integral of the given function at y squared from 1 to a. This time it's dy, not anymore dx, meaning with respect to y. Okay? So if you try to look at it, it's very tempting to estimate the value of your upper interval or upper boundary. So if you wanted to be sure about this, since you know its corresponding x, you can just substitute this value of x to the given function so that you would know its corresponding y value. So if you do that, you will get a certain y value equal to 5. That means at 2, y is equal to 5. So we are now very certain that the upper boundary is equal to 5. Thus, we can now improve our notation. So it's now pi times the integral of the given function at y squared from 1 to 5. And using your calculator, we can get the value 25.13 cubic units or units cubed. Let's have another example. This time, the volume of the solid form by the revolution of y equal to fx about the y-axis will now be given this particular notation. So if you try to look at it, it's just the same, only that we are just changing the function. Instead of x, it's now y. Okay? All right. Now, before you try to proceed in this video, I'd like you to pause this one, try to do it on your own, and then afterwards check if your answers are correct with what will be given here. Okay, let's proceed. So again here, we are to rotate it about the y-axis. Thus, it will give us this particular format. All right. So from here, we need to find the function. Now, unfortunately, we are not given the function. Thus, we have to derive it out from the graph. Since it's a linear graph, remember that we can actually come up with a function, or we can write an equation of from a linear graph using the slope-intercept form y equal to mx plus c. So in this case, we need the value of the m, by which from the graph you can get that value equal to negative 4/3. And the y-intercept is the point at which your graph crosses the y-axis. Thus, your y-intercept here is equal to 4. So remember, y-intercept is the value of your y when your x is equal to 0. Alright? So we now have y equal to mx plus c, y equal to negative 4/3, your slope x plus 4. Now, since we are rotating it about the y-axis, we have to find an equivalent function in terms of y. So we have to do algebraic manipulation here. All right. Therefore, our function in terms of y would now be this. Okay. So since we now have a function, we are now ready to find the integral, or we now are ready to find the volume of the shape or of the object resulting from rotating this particular curve along the y-axis. So it will just be equal to pi times the integral of the given function squared from 0 to 4. Again, using your calculator or by means of GDC, the volume is equal to 37.70 cubic units. Now, question is, how about if you are to find the volume resulting from area between the curves or between two curves? If you try to recall in my previous example, the area we're looking at is always a curve, either compare that with the x-axis or curve that with the y-axis. This time, how about if it's between two curves, meaning not anymore between the curve and the x or the y-axis? So for you to be able to find the resulting volume, we need first to do a sketch. So let's sketch the graph of this, and hence you will get this one. So here you're given already the intersection, the point of intersection. However, if in case you don't know the intersection here, you could actually find it using your GDC. That is actually part of our previous lesson. So if in case you have forgotten, try to revisit the previous video that we have had and try to see how the intersection was derived using your calculators. Now suppose you are not asked of the area, but you are asked of the volume of revolution. So given this particular area between the two curves, rotate it about 2 pi, or rotate the curve 2 pi about the x-axis. So if you do that, this is actually quite difficult to imagine because this shape is irregular. But then if you are going to rotate that, you're actually going to come up with this particular shape. Okay, this is not exactly the same curve, but then more or less the shape is the same. Now, if you try to look at it, since this is the only part we are focusing in, when you rotate it, you expect that this portion here, which is not part of the region between the two curves, meaning this is empty, because we're looking into this particular area, the area between the two curves, right? So the region below is empty. You expect that when you rotate this one, you will create a 3D object at which there is a portion that is hollow. Hollow meaning it's empty as well. There's nothing in it. Comparing it to the previous example wherein we are looking into the curve and the x-axis, everything is actually considered. The area from the curve down to the x-axis, since it's considered, when you rotate it, you come up with a solid object. But here, since we have a portion below which is empty, not considered, when you rotate it, you come up with a volume of an object by which the one in the middle is also empty, or we call it hollow. Okay, so the question now is, if this is the case, how would you find the volume of this particular object? Okay, so you don't have to worry because the process is exactly the same. Meaning, how you found or how you will find the area of the region under this curve would be the same procedure or would be the same stepping stone in order to find its volume as well. Recall, how do we find the area between two curves? It will just be the integral of the topmost curve minus the bottom curve. Or if it's along the y-axis, it's the area of the region under the rightmost curve minus the area of the region under the leftmost curve. That is if it's along the y-axis. In this case, since this is along the x-axis, we are rotating it about the x-axis. So it must be the area of the region underneath the topmost curve or the upper curve minus the area of the region under the lower curve. Okay? So recall, this is what we did last week. So the area will just be equal to the integral of the upper curve from 0 to 1.29 minus the integral of the area of the region under the lower curve from 0 to 1.29 dx. Okay? But since this is not what we're looking for, since we're looking for the volume, in other words, we can just simply convert this into a volume by using this as a function and this as a separate function as well. In other words, if we are after of the volume of revolution, then this will just simply become pi times the integral of the function squared. So if you try to look at it, this is just the same. Wait for a while. I think there's a mistake here, sorry. So for the area, this must not be present. This one as well must not be present. Okay, so again, to find the area of the region underneath the two curves, it will just be the integral of the function, okay, cosine of x from 0 to 1.29 dx minus the integral of the function e to the negative x from 0 to 1.29 dx. Now, if you wanted to find the volume instead, so we can use this as our function and put it into the formula for the volume. So we now have the volume of the function squared from 0 to 1.29 times pi minus the integral of the next function, the lower curve, squared dx from 0 to 1.29 times pi. So basically, it will just be the same. So how you found the area would be the same as how you would find the volume. All right. So since the pi is constant or this is common among the two, we can just factor it out. So this will now be equal to pi times the integral of the function squared from 0 to 1.29 dx minus the integral of the function squared from 0 to 1.29 dx. All right. And using your calculator, you can now find the volume, which is equal to 0.993 cubic units or units cubed. All right. Now this time, let's try to differentiate. So the previous method I said was actually what we call as the disk method because of the floppy disk. For the second method, we actually call it the washer method. Now you might be wondering why I'm introducing this. It's because if you try to search online or if you try to read your book, the book actually mentions disk method and washer method. So when is a washer method applicable and when is a disk method applicable? I'd like you to compare the difference between a washer and a disk. So for a disk, if you have seen a floppy disk, for example, floppy disk is actually solid all throughout. There's a hole in the middle, true, but then most of it is actually solid, or there's no portion which is empty for a floppy disk. But for a washer, if you try to look at it, there is a portion here in the middle which is actually empty or hollow. And this actually pertains to the functions that you are trying to revolve or rotate around a certain axis. For you to be able to see it clearly, let's try to compare the two. So if you try to look at the disk method, if you try to look at it, the corresponding result, the corresponding object is solid all throughout. But for the washer method, which results from rotating an area between two curves about the x or the y axis, since there's a portion below it that is empty, you expect that when you rotate it, you will also create a hollow part along its center or in the middle. That is why its shape looks like a hollow. Its shape rather looks like a washer. That's why we usually or most mathematicians would call it washer method. So this is the difference between disk method and washer method. So this time, I'd like you to open your books to page 507 to 508. So I'd like you to answer exercise 11I. And then afterwards, I'd like you also to go to Google Space and try to do your worksheet.